ठीक है, should we unmute this? Then ठीक है, okay. Let's start then. Still my display. Why is it glitching? Okay, hi. Good evening, everyone. Sorry we got started a little bit late, but it's a difficult weather in Bangalore. I mean, after a long summer, Bangalore is finally in its rainy element. So hope you guys had a decent travel. It was a place difficult to find. Did you guys have normal travel over here? All good? Okay, all right, perfect. So let us start the session, founder mode. Quick recap, is this the first time you guys are attending this session? Have you guys attended this session before? Have you seen online LinkedIn, any of the previous sessions before that? No, okay. This is the first time, right? So a quick introduction to Founder Mode. This is a series of hardware workshops that we're conducting, and essentially today's session is the third session in this entire series of four events, and we are today's session is the third session. I'll give you a quick recap about the other two sessions as well. Just a second. Hi. That should be fine. I think. Yeah, hope it doesn't glitch anymore. Okay. Right. Hi, everyone. So my name is Purvendra. I'm from Brahmworks. This is a quick introduction to myself. I'm an engineer by education, by heart. I'm an engineer, and I started an internship in a company called Proto 3DP way back in 2016. And from there, I picked up all my interest in hardware, started tinkering with things, mechanical, electronics, started building things, and incorporated company Brahmworks in 2017. At the time, the new upcoming things were in 3D printing, fast PCB development, rapid prototyping, and using additive methods like DLP, SLA, and so on. So these methods were something that we have, taken at heart in our company, and we started developing our entire company from there. That was just 1 year before I graduated. So I graduated in 2018 from bachelor's. By 2020, we had about $1 million revenue being bootstrapped. So as in startups, being bootstrapped is a challenge. So we continued our journey being bootstrapped, and we reached a 1 million revenue in 2020. In 2024, we launched Brahm AI. This is one of our own engines, which is geared completely towards hardware, generative hardware development, generative firmware development, and segmenting PCBs and segmenting technology into different areas. So this is Brahm AI. And this year, we are at a scale of mentoring about 5 startups to scale. So in the space of edtech, fintech, health tech, meditech, and everything, we are mentoring about 5 startups along with their incubation journey into the hardware space. So that's us. Here is a quick recap. Okay, so this is a quick recap of the first session. So as I mentioned, this is the third session in the entire series of 4 sessions. The first session we focused on what is an MVP and what is a proof of concept. So there are two things. One is a proof of concept. One is an MVP, which is a minimum viable product. We discussed about how you can understand the market, how you can talk to your users, what are the necessary inputs you need to collect. Let's say all of you would be interested in developing a product, either it's a full stack product or a hardware product. You would be interested to develop a product of your own or for somebody, right? So understanding how you develop a product for a market that is required, then analyzing the competition. So for example, if you're developing a mouse, you would probably understand the competition, what sort of a mouse you want to develop and so on. So you would definitely be interested in understanding the competition. Here is where we differentiate between what a proof of concept is, what an MVP is, what are the features of proof of concept, what you should focus, how you should ideate, and what are the frameworks you use to prioritize your features. Then what is the necessary documentation? Who are the stakeholders? Let's say you have buyers, you have your distributors, you have your designers, you have an entire market. So how do you document all of these so the entire product development is in a single, single alignment? The second session was balancing constraints and innovation. So we understood how do you balance a time constraint, which is essentially if you have a very short time to develop a project, how would you do it? If you have a very small cost budget, how would you develop a product? And if you have a performance constraint, how would you develop a product? So we looked at different frameworks like biomimicry. We looked at frameworks like house of quality and how you use these frameworks to enhance the product development under certain constraints. So today's session essentially is how do you build for scale and adaptability, right? So building a product one-off is different from building products for tens of thousands or a few 100,000 units, right? So today we understand what is the difference between developing a product for one and developing a product at scale. Right? So you must have heard these terms, right? What is a prototype versus what is a market ready product, right? So you must have come across these devices. So can anybody guess what is it that we are trying to prototype and build here? Sorry. It's a VR headset, right? Okay. So the difference between prototype and market ready is you essentially have a certain set number of differences, right? What is different? Your purpose is different, which means the purpose of a prototype could be to just understand the form factor or understand what is happening, but purpose of a market ready product is to sell it and give it to the final users. The process is different. So you must have heard of processes like 3D printing and fast rapid prototyping. The prototypes are usually done in a different process, and the production on a market ready unit is done under different processes. So they are done under various processes like forming, injection molding, and so on. So you have a difference in the process that is used for manufacturing at scale, right? Then comes complexity. So usually a prototyping complexity is lesser, which means you have a set number of components. You have 5, 6, 7, 10 number of components. You're trying to put them together, and you're trying to make them work together. But when it goes to a complete market ready product, essentially what you're focusing is you're focusing on repeatability, you're focusing on cost, you're focusing on ease of assembly, and so on. So complexity at a scale is also different. Then comes material. The materials that are compatible for prototypes are different. You will use resins, you will use plastics which are in filament form, and so on. So you'll use much simpler materials. Whereas in product ready or a market ready product, you will use complex finishes, you will use more advanced materials, you will use, probably if you're building a healthcare product, you will use a food grade, medical grade material. If you're using building a product in the food space, you'll use a food grade material and so on. So your materials will be different. Then comes the cost of one prototype will be way higher compared to a market ready prototype or a production cost, and that cost has to be optimized if you want to give it for scale. Then there's compliance. You would have to comply to certain standards. If you're selling it to a particular industry or a particular user, you have to comply to standards like ISO, CE, and so on. Then comes the environment. So your prototypes will be under a different environment. VR will be, or let's say your, if you're using a VR, you would probably use it with very various head sizes, different conditions. Somebody will be sweating, somebody will be using it to play sports, and so on. So your environment conditions are different. So you have to design for that as well. And feasibility. So this is the most important factor. will the prototype be feasible to make? If you make something that's not feasible to build, it uses extremely complex materials, then you will not be able to sell it to anybody. You won't be able to market it, or you won't be able to sell it as intended. Right. So guys, if you guys had to scale a VR headset from 10 to 10,000, can you take a guess what would break first? Like, can you guys tell me what would go wrong first? If you have to scale a product from 10 to 10,000, what would go wrong first? Any comments, any thoughts, anything that you guys can come up with? So this is a working session. It's not just me talking. I want all of you guys to engage, and I want you guys to kind of come up with your thoughts, talk about the things that you have in mind, because the way we engage is, you will also probably understand what is it that your thought process is going through, and you may discover a lot of things that you can talk about here today. So, yeah, if you guys can, like an example, right? Like if you're building a product with VR, right? Battery could go bust. Samsung Note even had their battery bust after 7 generations of development. So scaling, what could break, right? Batteries could go bust. Anything else? Hardware, sorry? Yeah, correct. Hardware might not fit together. Anything else?
The software needs calibration, it might be somewhat difficult with such a large number.
Yeah, calibration must be difficult for all. Anything else that you can think of? Are you going to sell all 10,000 in the same building? No, right? Logistics. It's going to break if you move the part from here to, let's say, US. Right? You have to figure out logistics. Anything else? Stock, inventory, things might go bad, things might spoil. If you keep a battery for long enough, it kind of depletes. You might have to keep charge in it. There's a lot of things that you have to take care when you look at, let's say, from 10 to 10,000, right? So understanding the scale is a whole different ball game altogether, and that's what we're here to do today. So, have you come across, how many people know this term DFM? How many people know the term DFM? You know DFM, DFM, nice, DFM. Good. So what is DFM, right? So the simple answer is it's called design for manufacturing. But where does it come from? So essentially DFM comes from a suite of purposes which is called DFX, which means it's derived from a certain purpose. So when you look at DFM, there are a lot of various things available in it, right? One is designed for reliability, one is designed for assembly, one is designed for repeatability, one is designed for assembly, designed for serviceability, then there is design for manufacturing also, right? So today we are going to be talking about design for manufacturing because that is most relevant to, let's say, scale and adaptability. But the others are also a suite of design frameworks and design principles that you need to use to ensure that your product doesn't go bust. Like we spoke about a few things that could go wrong when you scale up, right? To ensure that it doesn't go wrong in the way that we spoke about, we need to work on certain aspects, and DFM is one of the frameworks which helps you make your product suitable and compatible with large manufacturing practices. So this is one of the most important aspects, okay, and it enhances your product quality and reliability. Right. So how many of you here have heard Sony Walkman? How many of you use Sony Walkman? No, never heard. Did you? It's an old device, right? How many of you wondered how would you design a Sony Walkman? No. Would you be interested to meet a person who designed Sony Walkman? Yeah, right. So we have a very special person over here. He's our founder, Mr. Hari. He's a mechanical engineer. He's a tinker by heart. So he is a person who has been through manufacturing and designing very small parts which are handheld devices like, so let's say the Sony Walkman, all the way to ventilated machines and healthcare devices. So he's been part of companies like G Healthcare, Sony, HP, Agilent, Iva, and so on. So like huge companies all across the world. So he's here, and he will be helping us in understanding what are the things that we need to take care in design. So when it scales up, things don't go wrong, right? So his experience over here is something that is going to be crucial. So let's welcome Mr. Hari. Over to
Good evening,
you.
guys. So,
Yeah. I'll
uh,
just hand this over
we
to
are talking
you.
about DFM, right?
You
Design
can
for
stand here. Yeah.
Manufacturability.
Stand this.
Uh, well, it's a very big subject to be
I'll just
thrown
hand this
away in
over,
half
pass
an hour.
around. You can take a look at it. Just pass
Okay,
around.
so design for manufacturability basically depends on the processes what we adopt. You can design anything and everything, and it can be manufactured one way or another, but at what cost? That's the most important question any designer has to consider when you design. So you should understand what is the manufacturing process you're going to adapt for in your design. So when you're designing a plastic part like this, okay, injection molding, what is about the quantity? Or what is the cost per part? You can also 3D print it. But what is the cost? So every time you think about design for manufacturing, there's a relationship between the process and the material and the quantity and the cost. Are you on page with that? Good. So today I'll be concentrating more on injection molding because that is the most rampant part which is used everywhere in most of the places. Uh, Rather, plastic you can do injection molding, you can do forming, you can do vacuum forming, you can do calendering, you can do blow molding, lot of other processes, right, to get your plastic part. But if you understand injection molding, you will be able to correlate this to most of the other processes. Or you can do the same question into other processes and see whether you can incorporate the results in that. Right? So, quickly going on, this is a small part which we thought helps us understand.
इतना हाथ हिलता है ना कभी कैप्चर ही नहीं हो पाता ढंग से
Core cavity.
हाँ
Nobody? Yeah,
I got a mold and then you take it with let the plastic cool down.
great. Yeah, that's good enough to know. So you have a mold where plastic, you inject plastic material and the plastic cools and it comes out, right? Ejects out. So when we design a plastic part, what we came across generally is people just do a CAD model of the plastic part, but people really don't understand what are the limitations of the part and what are the defects in the plastic part. Say you have defects like sink mount, floor mounts, what do you call it, orange peel, and no fill areas. So let's work first in this particular example. This example is a norm, so you can understand what I'm talking about. So when you make injection molded part, right, there are certain guidelines you need to follow regarding the wall thickness. Generally, the part has to be of uniform wall thickness, but some places it calls for varying wall thickness, right? So when you have a varying wall thickness, never make a abrupt
They are
change.
sir logo.
If you do
Just
abrupt
galas on.
change, you will have
Skin color.
advantages and change in parameters of dimensions. Now in this particular part, if you have a injection molded part, now you see you have 30%, 50%, 70%, these are ribs built.
Just wear this.
So you have ribs built in the part. Then this is why do you have ribs? To increase the strength of the part. Right?
Just let him hold it in his hand.
So sometimes
Just let him hold it in his
have
hand.
to decide what should be the thickness of the ribs, what should be the height of the rib, and why the ribs, how many ribs to go, based upon the requirement.
Just also hold this. Just hold it in your hand.
Cannot hear? I thought I was loud enough.
No, this is for. It's okay. Just hold it in your hand.
So the basic rule in injection molding is the rib thickness should be less than 50% of the wall thickness. Why is this so? Any reasons? Anybody? No? Okay, if you have rib thick more than the wall thickness, what happens is you will get sink marks here. I think you can see in the part, right? Instead of a flat part, the part goes along. it deforms. I mean, you don't want to see a deformed part when you buy a part, right? You need a very good, crisp part, clean part. So this is one of the major defects found in most of the designs. And the designers leave it to the injection molder or the mold maker to solve this. They cannot solve it. You're going to solve it as a designer. Next is again the wall thickness, the polymers, right? Whether it is crystalline polymers or amorphous polymer, you are injecting material at 160, 180 degrees C, and you're cooling down to around 30 degrees C. So the polymer cools. The molecules come together, and they start warpage. So we have to avoid all hot spots in the mold and reduce the wall make the wall thickness almost equal to this one. See what happens when you do this, right? When you have a part like that, right, you have a, right here you have a very big lump of area compared to this wall thickness. You understand? So this will start pulling, and you will have a sink mark over there. So you cannot leave it to the mold maker or injection molder. It's basically a design fault that you're not given enough thought to it. So generally you've got to make these grooves so that your volume is still equal to the volume of the wall thickness. Am I on page? Understand? You are mechanical engineers, right? No? Okay, some of you are not. Okay, electronics. Sure, not an issue. Then undercuts. Okay, for electronics, we'll come back later. For mechanical engineers. So, do you know? So, if you want to make a hook like this, what makes sense? So, if you have a part like this, and when you do injection molding, you require a slide for this to move. A slide has to be there to move the part. Whereas a design like this, if you core out here, you don't require a slide. So, your tool complexity becomes lesser, the tool becomes cheaper, your part cost becomes cheaper. Ultimately, it's the cost of the part. Similarly, somebody puts ribs, cross ribs across the full part, and because of the same principle of more wall area, it's more shrinkage over there, more chance of getting sink mark on the behind surface. So you can eliminate easily by putting a profile like this so that the three junctions meet instead of four. So core and side core. So electronic guys will tell, okay, I want a hole for the wire to pass through, right? So the designer just puts a hole there. So what happens? Your mold becomes more complicated. You're going to use a side core to pull out make a hole. Whereas if you have a slot like this, it's much easier. You don't have to put a side core. It's straight core and cavity moving up. So again, the part becomes simpler. The mold becomes simpler. The mold cost reduces. The part cost reduces. Another thing is whenever you have a round hole, you have a weld line where the two plastic meet. That also creates an issue because you can see this weld line in some cases. If you're a very keen observer, you can see that. And that, again, sometimes it goes to rejection because it can be seen. And that adds to the part cost. So again, this is again related to core and cavity. You understand the core and cavity. So you have a mold like that. So what is easier to do? Whether it's easier to do this way or easier to do this way for a mold? Any idea? So when you do a mold, right, the cavity side, if you do this, you're going to do EDM, you're going to do wire cutting, and then put a insert, it becomes much costlier. Whereas this is directly, you're going to do a EDM on the cavity, so it's much simpler. Am I too fast? Okay, simple engraving. Which is better? One where is embossed, engraved above, or one there is a depression? This one? This one is better? You're talking in terms of what? The mold cost or? Huh? We are talking about injection molding. So in the injection molding, for you to make this, that means there's a depression in the cavity. A depression in the cavity can be easily done by EDM process. Whereas in this, if you're going to do, you're going to keep this area high and rest of the area go down, right? So that increases the mold cost. That increases the product cost, right? Anything you increase the mold cost, it's a capital cost, but it adds on to your product cost finally. So it is important for you to keep in mind as a designer that cost is the criteria which plays a very important role. Whether it's a small scale sector or a multinational company, we look at $0.001 price of the part. And that into million parts will tell you what is the cost, what is the savings per year. Okay, this is a slender core. So what happens is when you have the core coming here, right, the core which forms this, you see this boss is kept right next to the edge of this one. The electronic engineer has told, I want the boss, my PCB as big as possible within the small area, right? So the mechanical engineer has put it right across. So what happens is, this is what we call knife edge. The mold becomes very slender. Over time, maybe 10 shots, trial 2, trial 3, that mold breaks over there. So again, it's waste of time, it is waste of cost, money, everything. So avoid things like this. And have uniform wall thickness. See, suppose you have non-uniform wall thickness, your warpage varies. The shrinkage varies between the wall thickness. If the wall thickness is too high and one place the wall thickness is low, the thicker part shrinks more, the thinner part shrinks lesser. So when the thinner part doesn't shrink, it tends to warp because it has got lesser force compared to the overall part. So that part looks like a puppet. So you got to avoid those stuff. Okay, this is just an example of the radius, what impacts on the, we put generally draft angle on the molds on any part. You're going to put 3 degrees draft angle on the cavity side to prevent the part sticking to the cavity due to the textures. So if you see here, this is a part with the 0.5 radius and 0.5 draft versus one with the bigger radius and a big, I think 6 degrees draft. So that tells you how the dimension varies because of the draft. The overall size would have been there, and then you give a bigger draft, the part size increases. I think that's the end of this. Yeah, I think we'll give you some, yeah. And any questions?
So you talked about saving cost by minimizing the mold volume.
Mold,
Volume of the material that makes up the mold.
yeah.
But by minimizing that, we are actually like investing more on the substance that actually creates the object, right?
Yeah,
So should we consider that to be of higher priority to save?
no. That actually the mold cost does not make a big factor in the part. When you remove the material, it's a few paisa, I would say. The mold maker will not even look at that as the cost. For him, it's almost a fixed, almost the same price. The material, the steel material you're calling about OHNS or whatever material you use, right? or the processing of that does not play a very important role as far as the part cost is concerned, or the mold costing. This one. So you don't have to worry about that. You saw any questions? Yeah, it does not. Yeah, well, once you make the mold, it's there for millions of parts. So it amortizes like a few cents. And I have not seen vendors increasing the part price because the steel material is more. Because it doesn't matter for them, because they take a much bigger block and then machine it. Yeah, Puran. Yeah. Thank you, thank you.
Right. So let's all thank Mr. Hari for his valuable knowledge, and you all must definitely be, getting a bit nostalgic that these devices were there back in the day, and these technologies were, used at least, a few decades behind, and that sort of knowledge will help us understand how to reduce parts and everything, right? So why don't we do a quick exercise and keep this session in a way where it's more interactive and where you can understand, right? I'm sure you guys have a lot of doubts in your mind and things like what's happening, why should we even understand this, hey, I'm just going to build a small product, it's not, what's the relevance of a scale? Yes, you definitely, we can build great circuits and we can definitely build amazing products, but unless you can pack it in a certain way, you can ensure that it's built a certain way, it's assembled a certain way, it's sent in a certain way, it reaches a particular way to a particular user, that product has to be used in a way it's intended. So that's the most important factor of understanding why designing for scale is important. So what we have here today is a simple example. Okay, I have a part here which is before DFM, which is before design for manufacturing. So take a look at this design. I'm going to circulate this around, and I want you guys to, this is the same image on the screen over here. Can you guys tell me what are the things that are not optimum over here, or what are the things that could definitely increase the cost of the product? Please have a look. This is the physical part. This is the image. You guys can start with whatever. You might have seen a lot of things in this previous slides. You might have seen a few comments in terms of plastics and parts and whatnot. So can you guys take a quick look at it and tell me what is it that can be optimized in this, or what a DFM sort of a mindset or an activity should do to this, right? Has anybody 3D printed parts before? Yeah. What have you 3D printed? What materials have you used in 3D printing? PLA, ABS, yes. Anything else? How many parts have you printed in like a particular design? How many can you 3D print in a day? If let's say it's that size part. 3 or 4, yeah. If you produce for an entire year, that's like 1,200 parts, right? How many parts? I mean, 1,200 parts a year is not sufficient. Do you know what's the capacity of an injection mold machine, like a 100-120 ton injection mold machine, right? You can do a few 100,000 parts in a month, right? A few lakh parts in a month easily. So you definitely cannot produce those huge volumes in a process like 3D printing. So which means that the design that you use for 3D printing cannot be the same design that you use for an injection molding machine. All right. So if you guys can look at some of these features and tell what could what could be potential problems when you take this for molding. Yeah. Okay. Yeah. Wall thickness. The wall thickness you're talking about? Wall thickness. Yeah. Okay. So actually injection molding can support very thin walls as well, but the important factor, like sir mentioned over here, is equal wall thickness, right, or uniform wall thickness. So you need to maintain uniformity all over. Of course, strength is a issue. So if your part needs a lot of flexibility, sort of a strength, then in that case you have to give like a higher thickness. But thin wall is not necessarily a problem. If it's a thin wall amongst a lot of thick areas, then that thin wall will the non-uniform wall thickness will start creating an issue. So that's a very good point. Anything else you guys can think of? Someone was talking about lot of material in the part versus lot of material in the mold. Do you not see unnecessary material over here? Any excess materials over here? Any way this could be thought of or redesigned that the material used over here is lesser? Okay, very good question. That's most important to understand why you're building an enclosure as well. So this is a circuit, this is a battery, and this is a heat sink. So heat sink sits behind this. This place will have a battery, and this is a PCB, and this is a USB hub. So essentially, it's a PCB enclosure, right? And these are points to mount it on a wall or a frame or something. So it's just a PCB enclosure. Yes, they are. They are very complex. Yeah, very true. They are very complex. Anything else?
This design seems to be for an environment that is very harsh. So if it's not that, we can maybe like cut off quite a lot of material from there.
True. Yes, you can optimize material. That is true. Right? Okay. So here is the final injection molded part that is being sold. Take a guess how it looks. This is how it looks. This is it. This is all you need. Right? I'm going to circulate this parts as well. So this is the end result. You can flip it around. So this is the final injection molded part, and this is all you need, right? See, wall thickness is equal everywhere. These ribs are all similar walls. Okay, if you see the thickness over here is constant everywhere. There is radius, right? I think in the parts that were given previously, radius was mentioned. Core cavity concepts were mentioned. This is far more optimized, far more planar and simpler, where it makes the tooling easier because the flow of the materials are easier and so on. So this is the final result of a part that has gone through an exercise of DFM. So which means that this has now been designed for manufacturing, and when you produce in scale, you will not see many defects in the part. You will not see, if you build like 1 lakh units or you punch out 1 lakh units, all of them will be same, right, within their own tolerance and limits. If you take out the circuits from one and assemble it in another, it's going to be same. It's going to be the similar part, and also the cost is very optimized. Now here you see the most minimal amount of material. You really need only so much. You don't need more than this for the purpose, right? I still can press fit a battery, press fit a PCB, press fit a heat sink, the USB device, cable is going to come out. Everything will still work exactly as intended, and definitely better than the prototype, because this is now going to be a stronger part because the plastic is stronger than the 3D printed plastic. So this is an exercise of DFM, and you guys can definitely go keep both the parts side by side and kind of take a look at what. Yeah. Yeah, it will be for the same thicknesses. Because even when you go 100% infill, there are gaps, right? So if you know lattice structures, there will still remain gaps in 3D printed areas. Plus, the fusion is not as strong as an injection molded part. They are done at a very high tonnage pressure. So the polymer bonding is very strong in an injection molded part. If you take a same wall thickness, same plastic, let's say ABS plastic versus ABS plastic, definitely it will be strong. 100% infill really doesn't guarantee much of a strength anyways. It's just consuming material, but you will still have certain gaps and layers, right? Because of layered adhesion, it may still separate out under a lot of forces. So, but that will not happen in injection molded part. Anything else? Do you guys have any other questions, doubts, queries? Right. So we'll do a quick wrap up of this entire session. So today we have understood what a prototype is and what a market ready product is, which means that you have understood what are the different processes, different purposes, different materials. We've taken a look at what are the difference in cost, compliance, requirements, and what are the thoughts and the design methodologies that we need to implement to ensure that a prototype is then converted to a market ready product. Right? We've seen the principles of DFM, which is understanding that we need to keep the components at a very low volume, minimizing the components, standardizing certain things, making it compatible. So we have understood the principles of DFM. We've gone through an entire DFM blueprint, which will tell us to focus on certain areas which will either increase your efficiency, reduce your cost, or even make the entire assembly and make the entire product simpler to use. So this is a quick wrap up of the entire session, and yeah, that's about the session. So thank you guys for having this session. So next we have Srinivas. So Srinivas will be talking about DFM and scalability and adaptability as well. Thank you.
I just want to see if it's getting disconnected. It's not getting connected. Hello? No, no. That's not okay. Somewhere. Okay. Hey, hi everyone. So today I'm going to have a very casual conversation about scaling and adaptability. So I hope most of your students here. Okay. So let's say you want to build a product, and specifically you want to build a hardware product. So that is what we are going to talk. How we're going to start building a hardware product, or basically electronic product, and you're going to scale it like in millions. So that's what, like iPhone or any laptops you see, right? It's not manufactured in a very small scale. It's usually a very very large scale, and it will be happening in the scale of like 1 million to 10 million units. So there are a lot of challenges while making a very huge scale. So that is what we are going to discuss today. So before that, I'll just introduce myself. So myself Srinivasan. So what I do is we are trying to build India's largest hardware ecosystem. Basically, if you have heard about Arduino, Adafruit, or SparkFun, something similar to that we are trying to build. But our core concept is we want to keep it like more modular and also completely made in India. That is our concept. So apart from that, we are also trying to build an online community where we have a forum, we have all the tools that's needed for engineering and all those other sort of stuff. But today we'll be tackling all the hardware challenges that I went through personally to build a product like this. And also like I've worked on other similar products in the previous works. So I'm just going to showcase some examples, and I'll show you how those products were scaled. And some of them failed as well. It's not like whatever you build is going to succeed. So I'll show you both my failures and also like building a very successful large scale products. So I'm not sure if you guys have been here before, but this is my second session. So the first session we had a talk about path selection and how to optimize the design. Basically, because India is a very price sensitive market, if you're building something, it has to be very price sensitive. It's not, you can't make something that people are not going to afford it. So last talk was most about how to select a part that is more cost effective and how to optimize design. Basically, while designing itself, how to reduce your cost. Then we had something called panelization. So basically, instead of making one particular PCB, so we'll put everything in a single panel and then we get it manufactured. And finally, we had like automation process, like how to automate testing, how to automate like functional testing and other stuff. And also we talked about line circuit itself, like how to place order on line circuit, how to do part selection, and how to place order, and other stuff that is related to the online portal. So that was a recap. So if you want to do that recap, or if you want to see that, we have a website. So if you go to pcbcupid.com/post, so you land on the site, and in the site, if you want to take a photo of that, you can take a photo of this, so that QR will directly take you to the site. So basically there we have all more information about whatever we talked on the previous session. So I think that is not published yet, but we can publish it by today, as well as combining whatever today's session we are having. Both the session will combine and we'll publish it here. But apart from that, we have other more information related to manufacturing and related to product design in the website itself. We have an article section for that. So today's major topic will be the scaling and adaptability. So scaling works differently for different units. Let's say if you're building something for 100 units, the way you're going to build or design is going to be different than building something for 1 million units. So that is going to be completely different than building for 100 units. So I'll just give a very simple example. So this is a 100 unit, and that is something done for say close to 3000 units. And you can see that is a different scale altogether. That is something that you are building for 5000 units or 10,000 units. So it is going to be a lot of struggle, as especially if you have a very small team, or like if you are trying to build everything on your own. So initially I have to learn it in the hard way. Then I thought like it's much easier to scale. You can't design something and expect it to like automatically keep scaling. So it's not something you build for 1000, it's not going to work for 10,000. Same thing, if you build something for 10,000, it's not going to work for 1 million. So all these factors you need to consider before you try to scale. So that is what we are going to completely discuss. So there are like 5 different stages. I'll walk you through all the stages, so you'll have an idea about how product is scaled, or especially the electronics product is scaled worldwide. So this is a very similar process everybody follows, and that is what we're going to look into. So first is component life cycle. So especially when you're building for like say 100 units, right? It's going to be very easy. You can go to any random website. Even most probably you'll find even Amazon. Components you find in Amazon, usually they'll have a stock of 100 units. So you can easily get that 100 units and build your first 100 products. It's very simple. So you don't have to talk to many people. You can easily source online. And also the channel, how you source is not usually a big deal. Most of the time you get it together and put together, they'll obviously work. Once you do this 100 units, the challenges start as you keep ramping up. Let's say you want to go for 1 unit. At 1 unit scale, you need a traceability. So traceability is like you get one single component, you need to have more detail about that single component. Let's say where did it come from, what was the cost, and you want to track what time it was manufactured, what batch it was manufactured. Because out of 1000, let's say if you have a failure rate of 30%, so you need to get to know where this failure is happening. Is it because of your manufacturing design, or is it because of the manufacturer itself, the component whoever is manufacturing, right? So to identify that, you need a traceability. So that's why you can use like line circuit. Also they have their own parts page. There also you'll find all the components which are easy to trace. Basically you can go back and you can reorder, or like if you want to track what that particular component is, all those details will be there. And let's say you want to go beyond 1K, let's say 10,000 units. So in 10,000 units, the challenge keeps increasing. So in 10,000 units, you can't randomly select a part now. So in first case, you can select any part, put together, you build a product. In second case, you just need little bit of traceability so that you can recurringly build to some extent. So you don't have a very large audience base. Now at 10K units, the problem really arises where are the manufacturers, so the distributors, do they even have a capability to have 10K units of those components? Let's say we are getting one resistor and capacitor, or I think that's easy to find. Let's say we specifically get one particular IC, And that particular IC usually will have 4 different stages. One is called pre-release, then we have something called active, then we have something not recommended for new design, and finally we have something called end of life. So I'll just quickly walk you through all the 4 stages. Pre-release is something like a beta launch done for the IC itself. So let's usually we don't see this in a public use case, because whatever they want to release, because they release it at very large volume, they want all their ICs to be very well matured. So this is not usually seen in a consumer devices. But pre-releases are something that is sent to developers. Like suppose I'm building a product, I want to learn more about that product. In that case, we get the pre-release. Even before the launch, we test with that and try to figure out how to build products around it. And then something called as active. Active is what everybody's used for production. Suppose let's say you have a product, let's say you're building a mobile phone, and you want some component of the mobile phone to be always in active stage, so that you can keep recurringly procuring it every now and then. So that is a active. And next is not recommended for new design. So what do they mean by is the manufacturer itself, they let you know, please don't use this because this is going to soon phase out and they'll launch a new product. So that is not recommended for new design. And finally we have something called EOL, or end of life. Here what basically they're telling is, that's it, the product is done, we are not going to manufacture it anymore. But the thing is, sometimes some distributors or vendors, they'll still stock it and they'll have the, so you need to make sure you check in their manufacturer website if it is actually end of life or not. Because let's say you talk to a distributor, they'll tell you, okay, this is still available, you use it and you're using it and you're manufacturing the first 10,000 batch. But when you go back to them and say, I want another 10,000, they might not be able to provide it. So that's a very difficult thing. So what you have to do is make sure you check the manufacturer website, or try to contact them and find out if the part is in end of life or is it in active process. Then comes the 100K unit. Now this is a scale where you are targeting like a very large audience base. Let's say you are targeting like a whole India. So basically 100K, that's like a very small sample size, but still 100K is a very good number. In this case, what happens is, even that whatever you see on the website is not enough. You need to have more connections, and also you need to, if possible, directly talk to the manufacturer itself. Like that's what I mean by Texas Instrument, Qualcomm, and MediaTek. Let's say if you want to build a very small device and you want to use Qualcomm or MediaTek, nobody will give you Qualcomm and MediaTek, because it's very highly IP rated, and also like it's like very highly protected. So you need to have a minimum threshold value for them to provide you support, and also give you all the access to their internal documents and all. So for that, the minimum unit is 100K. And this is the same thing for some Chinese chips also, not just for like big brands. So whichever ICs you see, especially like these processors, right, they're very expensive. So they don't support for small players. Instead, they support for only large players. So in that case, we go for the 100K units. Finally, we hit the 1 million mark. So in 1 million mark, what happens is, this is now something beyond a small area. So it's like you're targeting worldwide. So in that case, you will be manufacturing 1 million units. In this case, you need to have a very, very close tie-up with all the manufacturing plant itself. Directly to every single component that is going to on your product, you need to have direct contact. You need to like talk and get the timelines properly. So let's say you talk to them and you tell them, at this time I need this many quantities, or they'll give you a timeline telling, at this time I'll give you this many quantities. So this kind of conversation you need to have when you're reaching 1 million units. So that is mostly about how to select the component. So you need to think about all this process while selecting a component based on the scale what you're doing. So there are other things that is related to component itself. So when we go for design optimization, we'll see what are those processes. Next is supply chain and logistics. So this is another project. So here we have like 100 units versus 50 units. So you can see the scaling, right? So this is the 100 units. It's in a very small area. But when you see a 50 units, it is taking a very large area. So basically, what you need to think about your product is not just the quantity or the money that is involved. Also, you need to think about the logistics and also the warehousing. So where would you manufacture and keep it? So are there people ready to buy your product? So you need to think about the cost for warehousing. You need to think about the cost for shipping, and also you need to think about the labor cost, who is going to handle it, and like, do you need machineries to move the products? So this was something very small. Let's say you're building something of bigger things. Let's say you're building a coffee machine. So think about having 1,000 coffee machine. It's going to be very huge, and you are going to have a very huge resource constraint on supply chain and also warehousing. So you need to consider all this even before you build the product. Only then you can decide what volume you can manufacture initially. Either you're going to do at 1K or you're going to make it at 100K. And do you have enough money? Do you have enough manpower and all those things? So this is like building at different volumes. So that is at building at a 5K volume, and to some extent, we'll say you can manage by yourself for 10K volume. Again, that 10K volume depends really on the size of the board. But usually the 10K volume, even for a small board, is going to take a lot of space, even for a small product. But for a bigger product, it's going to be very difficult. It's not something that easy to manage in a very small team or built by individual. So usually in this case, what people do is they go for EMS solutions, basically electronics manufacturing solutions, to help them build all these things. So here the key factor is, what do you want to do? Whether you want to cost, optimize the cost, or do you want to control your product, or do you want to focus more on the business? Like you give all the manufacturing to somebody else, let them handle all. What you'll do is you just go do your business where you buy this and sell it. But in that case, you can easily scale where you don't need more people in your engineering team or technical team. Whereas if you go with the second method, where you want to control your product, you want to make your own design, handle every step along the way, then it's going to become very, very difficult. So that's what it's again comes to the cost, how much money you are planning to invest, and what kind of product it is. Based on that, you can either go for like a EMS solution, or you can build by yourself. That is up to 10K, what I was talking about. But again, the game totally changes when you go for 100K and 1 million units. In 100K, the warehousing cost alone is going to be very, very expensive. Just storing, not even after manufacturing, even before manufacturing, the warehousing cost is going to be very high for 100K units. Let's say let's say your board has some 100 components. Now each 100 components into 100K, that is going to be like more than 10 lakh parts that you need to store. Basically you become your own distributor. So that is going to be very difficult to manage. So you need to think about all this and how you are going to manage this. So usually the best option for 100K is like go with a EMS solution and get it done. So it's very easy. All you have to do is more focus on the design and how you are going to handle the 100K input. Now it comes to 1 million, again, the way you're going to handle will become completely different. Not from like 10K, 100K, 1 million will be completely different, because even storing 1 million units is going to be very difficult. The warehousing cost will be extremely high, even for very big players. So here what we do is, here there is something called time scheduling. So what you do is, instead of like trying to manufacture all the 1 million at one shot, you'll have a ramp up stage. You slowly start from 100K, and you take a timeline from the manufacturer itself and ask them to give you the component every 1 month, so that you don't have to spend a lot of money on the warehousing. So they'll manufacture exactly for 1 month, they'll send you have that, and you build 100K. Then they'll manufacture for the next month 100K, they'll send you the 100K, then you build the 100K. So this cycle keeps repeating. I'm just giving 100K as an example, but again, this time scheduling will be flexible depending on how much resource you have, how much money you're planning to invest, and also the warehousing scale. So next is, this is the most important stage, third one. It's about design consideration. So usually this design consideration stage is not taken into account while designing the product itself. So in the previous session, we were talking more about design optimization, how to make the circuit more optimized, where to put everything together. So here what we are doing is, the testing stages for say 100 units to 1 million units will completely vary. So for 100 units, the testing can be done in many ways. Usually what we prefer is just manual testing. It's going to hardly take, like in one day, you can test all the 100 boards or 100 units. Whereas now when you move to 1K, that is going to be difficult, but if you have more manpower, you can still do it. But what we recommend is make a very small jig, which you can help you to automate the testing process. Again, it's not very effective, but it's something much easy and low cost. Then for 5 to 25K, there is something called manual jig, where you have a labor force. They sit every day, they keep testing your each and every device, but the process will be a lot more optimized, and end of the day, you'll get a pass or fail result in that. And finally, for 100K and 1 million plus units, there is something called automated test jig. So here what happens is, it's similar to a conveyor system. If you see, there is a conveyor system here. So there, the devices will keep coming up, and it will be going through a testing device. So that will be your automated test jig, and the test jig will test your device, and it'll just, on the screen back there will be a screen. Here it will say pass or fail. So that is the whole process. And the most complex part about this is the testing jig itself is going to cost you a lot, because the testing jig will have a lot of mechanism and also self test. So it will try to figure out whether whatever the testing it is doing, is it right or wrong, and also it will see if it is going to break down anytime soon. And apart from that, the automated test jig also will have a very less error compared to the manual test jig. Maybe in manual test jig, the error rate will be little higher because it's manually tested by the human. The human error rate will be little higher. So next we have something called aging test. This is something that's very rarely seen. So here what usually happens is you run a device in a very closed room for like multiple hours. So all the audio, display, whatever is there, it will keep running random tests. For example, if you take a LCD, it will randomly keep changing from RGB values to see all the pixels, and they'll see a life cycle when that pixels are going to die. So that is the whole process. And the same thing goes for the LEDs also, and there are other products as well. So usually what they do is they just turn it on, put it inside a room, and they keep checking it now and then. So that is done for 25K. So less than 25K, that is enough. Like you often test it and see what device is failing and try to take a note down on that. But when you go for again 100K plus 1 million units, it's going to be very expensive to do manual aging. So what they do is something called automated aging. In that process, they'll just run this, and it will automatically calculate itself whether it is getting aged, and whenever it is going to die, there will be a record system. So whichever the device dies, they will keep recording it, and you'll get to know the percentage even without entering the room, how much is the aging time. Now, I think the best example more than this would be, just now I remembered. Have you seen the Flip, Samsung Flip? They used to do a aging test, which does that 200 times. So that is one of the automated aging tests where they do the keep flipping it like for more than 2 lakh times. So that is a very good example. Then comes optimizing the component itself. So this is what I was talking in the first stage. So there's more to optimizing and selecting the component. Here, mostly what we talk about is when to use a module, when to use a IC, and when to use a custom IC. Let's say you're building something like a very small unit, 100 to 10K units. 10K is also a little lot, but still we can manage up to 10K units. So these are like pre-certified modules. So if you see, it will have been CE certified and FCC certified. So when you use this, you don't have to get that certification again. So it is much easier to sell. But the problem is it's very hard to get. Again, say you want a 1 million unit, you need to talk to the vendor of the module to get that 1 million unit. So which is going to be very difficult. Next will come to 100K to 1 million unit. There you can just specifically find one particular IC. Let's say we are using ESP32 here. This is the IC that is used inside the module. So instead of this module, you skip this part, you directly go to use IC, and you use that IC to build your product. So that is much easier. It can go up to 1 million, 5 million, not an issue. Now, where the complexity is, when you try to build a product that is over like 10 million, you want to have more software control, you'll have a lot of money, and also you want to have a lot of hardware control as well. So best example would be Apple. So every end to end, from hardware to the software, they have a complete control. So if you want to build a product like that, that is when you go for something called as ASIC. That is nothing but application specific integrated circuit. So by using ASIC, you can build, for example, I've given us the M1 here. So similar to that, you can build a very specific IC and use that IC for your product. So that is going to be a very rare case, or only when you are trying to build a product that is going to go global, and also it's going to hit like a 10 million or 10 million plus mark. So next is optimizing the circuit itself. So basically what we need to do is we need to reduce silicons as much as possible. So we need to stop using any specific ICs that is going to like help you initially. So a very good example would be this mic module. So these are two different mics, but they do the same thing. The way this mic works is called I2S. So basically it will record the audio and it will give you in form of digital signal. Here the advantage is the designer will have less work to do. You don't have to implement any filters. You don't have to worry about the track lengths. You just put the IC, you connect it to your microcontroller, it will start communicating. But the cost of this is going to be like 200 plus rupees. And that is called a condenser mic. It will give you analog waveform. But the thing is, it's very complicated to tune the mic. So if you want the same quality what you're getting in this, you have to put a lot more effort into that. Let's say it is going to take you like 1 month and a lot of money to do that. Let's say 1 or 2 lakhs just to tune the microphone. But the thing is, when you're launching a product of like say 1 million unit, this is a much better option. It's much better to put a lot of money and time initially to optimize that one component rather than going for the second one. So again, this basically comes down to whether you're going to do 100k unit or 10 million unit or 100 units. So based on that, you have to make the selection whether to go for a easier design and give a lot of money, or put a lot of time and resource initially and get benefit later on. So next comes the certification. So initially, like, you don't have to worry about the certification up to 5k units and 100k unit, say 5k units. But the thing is, again, if you're selling to like any countries outside India, or even some cases like within India, you need to have a BIS certification. And other certification, if you see, we have CE, FCC, UL. So all these certifications are very necessary, especially when you are going anything beyond 100k. We need to make sure it is compatible worldwide. It is not just you're building for India. You need to make sure it is going through all the compliance process, and also it is being like a worldwide standard. So this is where it gets a little more complex during design process. It's called mean time between failures, or MTBF. So what this basically gives is how long your product is going to stay in the market, and based on this is what manufacturers give us the warranty period and also the serviceability. So this MTBF is a value that is given for even every single component. So whenever you're getting from the manufacturer, right, even they'll give you a MTBF or life cycle for that one particular component. So based on this, you calculate the MTBF of your whole product. Let's say using that MTBF value, you say your product is going to last for 5 years. Then you can easily provide a warranty period for your customer. Say, I'll give you a warranty for this for 3 years. And that is how most of the warranty works. So you'll know where things are failing as well. So let's say MTBF value of certain component in your product is very less. So even in some cases, if it goes bad, you can get it back, you can service it, and you can give it back. So that is the whole point of figuring out mean time between failures. But thing is, again, this is done something for 100k plus units. But in some cases, if the volume is less, but the cost of the product is very high, even in that case, we calculate the mean time between failures. Again, all this process from certification, MTBF, all these are very difficult and very very, very expensive process to do it as a very small startup or with a very small team. So usually what people do is they try to approach different expertise in this field. So you go meet a design house, or you find a EMS solution who will help you throughout the certification process or meantime between failure processes. So why this is important, I'll tell you. It's very simple. Let's say you're having a very small team and you want to build everything in-house. And even if you build everything in-house, you won't have enough work for the people to give. So whoever the expert you are hiring for the certification, right? Since you are making only one product, it doesn't make sense to hire him and just get the certificate and you can't fire him. So, but if you're a company like very huge, like say Apple or Microsoft or Google, so these guys have enough resources and they have enough projects that's running simultaneously. They can hire somebody dedicated only to do this, and they can be working parallelly on multiple projects. So that you have to decide initially, like whether to build the a team by yourself, and do you have like a timeline, not just for 1 year. You need to have like a goal for next 10 years. In that case, it makes sense to have the expertise in-house. In case if you are planning to do it only for once or twice, it's much better you outsource all this work. Okay, then fourth step is iterate to ramp up. So usually, like whatever we discussed previously, right, there are a lot of chances that not just lot of chances, usually there are chances people make mistakes during all this process, or basically learn from their mistakes. And also whatever the consumer, we are getting the input, right? So that feedback we take and we try to make a positive feedback loop to build a better product. So that is the iterate to ramp up basically. So what we usually do is we do the whole design and we go for a lab development. Where we build the prototype and everything. Initially we do something called as a pilot launch. So this will be like usually like 500 to 1k units that you launch in the market, and you see how the product performs, how many failures you have, and how to solve that failures, and how to do the serviceability. The best example for this would be like Aether. So if you take Aether, initially when they launched the Aether 1, which has a lot of problems, and also it was very expensive, but still people bought that, and like they use that vehicle to develop a better bike altogether. But you saw the time, right? Initially they were producing like hardly like 1,000 bikes. Now they are producing like 20,000 plus bikes. So that is the time to ramp up, and this again varies from product to product. Some products is much easier to ramp up. let's say from 10 product, from 1K to 100K can be done in like say 20 weeks or something. But if you take something like a vehicle, it's not going to happen that soon. So that is going to have a very long time frame. Whereas when I gave you the Ether example, you might think about other manufacturers like bike vendors. In that case, what they are doing is they already have all the expertise, all the product line, everything is set up. So they are using their in-house expertise to build it, so they can launch any product like within a year or within 2 to 3 years. So that is not possible if you are like a very brand new startup. And again, this is the workflow I told you, right? Even many companies during your full scale production, they'll remove the product out and they'll try to fix the product. That is what is going back, and then they'll relaunch it, or they'll launch something like a version 2 or like version 1.1, something similar to that. So that is the whole iterative process. Yeah, and this is very important. Lead time to ramp up and ramp down. So sometimes what we think is, whatever the points I told, you might be like, okay, I went through everything. Now I have money. I want to manufacture, say, 10,000 units. But this 10,000 units not going to happen in one day. If it's like 100 units, maybe you can find the parts and everything and like instantly happen. But 10K is going to be very cost effective, what to say? It's going to be very expensive. So in that case, you have to pre-plan everything. It's not going to happen in one day. It's going to take like 6 months, or sometimes it can even take a year if you want to hit all the 1 million units. So that is what we mean by ramp up. And what do we mean by ramp down is, so whatever you are manufacturing, right, you have to end of the day sell it to someone. So there should be somebody on the receiving end to receive all these products. So, but so many cases, what happens is you buy this and keep in your warehouse, and it doesn't make sense. So in that case, you have to ramp down, where you have to, throughout the supply chain, you have to inform that you are going to ramp down and reduce your intake, reduce taking your components slow by slow, and stop reducing your product. And towards the end, this is called end of life. So as I told, for the component, right, for every component there is an end of life. They calculate it in the same way. They'll see how many people are buying, and slowly people stop buying. That goes to end of life. Same thing for your product as well. So you start ramping up, and usually this is not just a bell curve. This is just an example, but most of the time, if your product is going to stay in the market for a very long time, it's going to go up and plateau for a very long time, and then it's going to go down. So that is called the ramp down, when your product is going into end of life. So this is the complete production, where you start from 100 units to 1 million units. So that's it from my side. So you guys have any questions, you can ask.
One question.
Yeah.
When you say this 1K and 100 units, 1K is okay, fine.
Yeah. Yeah.
If you go like 10K, 50K, 100K,
Yeah.
what is the normal timeline companies have for selling it?
Again, it depends on whatever the product you use and whatever the component you choose. Some components are like very widely available, like some LDOs, you can easily get up to 20K units like within 2-3 days, because usually distributors have that much capacity to have that particular LDO. But let's say you get like very specific part which is not in the market, then again that is going to take a lead time of 8 weeks just to get that one component. So that will be a problem. And also you need to see on the other end also, like do you have like enough labor to, in terms of like assembly, is it like a manual assembly, automated assembly, how we are going to manufacture PCB, how long the PCB will be manufactured, how long will it take for the, yeah.
What's the good approach? Do we stock it up or we do just in time? In
uh,
terms of silicon, for example, silicon.
Okay.
We want to get in advance, stock it up to something like what?
Yeah. 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 So in that case, it's very hard to tell actually. It depends on the product you have. So you think if your product has a market and you say, I'm going to sell 100K units for sure, then you can stock it up. But usually there is something, what happens is, okay, this happens in a very extreme cases. Let's say there is a product that you're selling for at a 10 million scale. So here what you can do is you can directly talk with the manufacturer and get a complete line only for yourself. So they'll manufacture only for you and for not anybody else. So this is what Apple or Google or any big companies, right? They'll have a product line with the TI itself. So whatever the LDO they're producing for market, they might not be producing it for them. The same way, whatever they're producing it for Google and other thing, they'll be not be giving it out for other consumers. So that's what it mostly it's around supply chain basically. So you need to decide if you have the volume to sell. Based on that, you can decide. Okay. Anything else? So if not, let's wrap this up.
Thank you, Shreema. That was a very nice session. Thank you. Thank you, Srinivas. Thank you, Purvendra, and thank you, Hari sir. We had a very interactive and very informative session today. So we're done with the presentations for today. We're just going to move into a small networking session, and we're also getting around some food. So please stick around for food and hang around. Everybody is still here. If you've been building products, we're very open to discussing those products. You can get some great feedback from these people, fellow attendees, even anybody from Brownworks or Lions. So stick around for a little bit longer. And as mentioned previously, this is going to be this was the third session of the FounderMode series. The last session is going to come up in, say, I think about 3 weeks or so. Since you've all signed up for this, you will get the notification for the next session. In the last session, in the next session, what we will do is we're going to tear down a product. We're going to take an existing product from the market. We're going to take it apart and see what are the components, how each thing fits in, what different factors do you consider while building the product. So we're going to go full into founder mode to understand how to build that product from scratch. Right? Okay. Thank you, guys. I hope you all enjoyed. If there is any feedback, please let us know. Okay. Thank you, guys.